Imagine a place in the cosmos so extreme, so utterly bizarre that it pushes our understanding of reality to its absolute limit. This is not science fiction. These places exist. They are called black holes. They are born from the deaths of the most massive stars in the universe. When a star many times more massive than our sun runs out of fuel, it can no longer support its own immense weight. The core collapses under its own gravity, crushing down into an infinitely small point. What is left behind is a region of space-time where gravity is so strong that nothing, not even light, can escape. This is the essence of a black hole. They are the universe's ultimate traps. We can't see them directly, of course. How could we, when they swallow light itself? Instead, we detect their presence by observing their effects on the stars and gas around them. We see matter being heated to incredible temperatures as it spirals into the abyss, glowing brightly just before it vanishes forever. These cosmic behemoths are found throughout the universe. At the heart of nearly every large galaxy, including our own Milky Way, there lurks a supermassive black hole. The one at the center of our galaxy, Sagittarius A, is a giant weighing about 4 million solar masses. In our everyday world, we are governed by certain fundamental rules. These are the laws of physics. One of the most important of these rules is the second law of thermodynamics. It tells us that things in the universe tend to move from order to disorder. Think of a hot cup of tea. It will always cool down, spreading its heat into the surrounding air. The heat never gathers itself back into the cup. This natural tendency towards messiness, towards a more disordered state, is called entropy. But then came the black holes, and they seemed to break this sacred rule. Imagine you take your hot cup of tea, with all its heat and all its disordered high-entropy particles, and you throw it into a black hole. What happens? The tea disappears. From the outside, it looks like all that disorder, all that entropy, has simply been deleted. This presented a profound puzzle for physicists. It was a genuine crisis. Could it be that black holes were cosmic outlaws, ignoring the most fundamental laws of nature? The story of how we solved this puzzle is a story of human curiosity. It starts with a young physicist named Jacob Bekenstein, who dared to ask a simple but powerful question. What if black holes do have entropy? Bekenstein proposed that a black hole's entropy was connected to something we could measure, its surface area. He noticed a strange similarity between the behavior of a black hole's event horizon and the behavior of entropy. It was taken up and explored by one of the most famous scientists of our time, Stephen Hawking. At first, Hawking was skeptical. He tried to prove Bekenstein wrong, but in the process of trying to disprove the idea, he stumbled upon something even more astonishing. He discovered that if you combine the laws of gravity with the strange rules of quantum mechanics, black holes are not completely black after all. They must glow, ever so faintly. This discovery, now known as Hawking radiation, changed everything. Have you ever wondered why time seems to move in only one direction? We remember the past, but we don't remember the future. We see a glass fall and shatter, but we never see the shards of glass leap off the floor and reform into a perfect cup. This one-way street of time is linked to a concept called entropy. The reason time moves forward is because the universe as a whole is becoming more disordered. Think of a drop of ink in a glass of water. The ink never gathers itself back into a single drop. To really understand entropy, let's think about something more familiar. Imagine your bedroom. When you have cleaned it, everything is in its proper place. This is a state of high order or low entropy. Now imagine what happens over the course of a week. The room naturally becomes messy. The key insight here is that there are vastly more ways for the room to be messy than for it to be tidy. This is the statistical nature of entropy. The concept of entropy operates on the grandest cosmic scale. Scientists believe that the universe itself began in a state of incredibly low entropy. At the moment of the Big Bang, all the matter and energy of the cosmos was compressed into a tiny, hot, and dense point. From that highly ordered beginning, the universe has been expanding and evolving for nearly 14 billion years. This cosmic increase in entropy is what drives all the interesting things that happen. Every star is part of this grand process. This leads to a profound question about the ultimate fate of the universe. The long-term forecast is a state of maximum entropy. often called the heat death of the universe. In this distant future, all the stars will have burned out, and the universe will become a cold, dark, and uniform soup of particles and radiation. The second law of thermodynamics was a cornerstone of physics. Scientists used it like a cosmic accounting system. You could track all the energy and all the entropy in any process, and the books always had to balance. This is precisely why black holes presented such a terrifying problem. When matter falls into a black hole, it carries with it all of its properties, including its entropy. From the outside, it seems as if that entropy has simply vanished. Jacob Bekenstein's idea was radical. He proposed that a black hole's entropy was connected to something we could measure, its surface area. Could it be that the surface area of a black hole's event horizon was not just like entropy, but that it actually was a measure of its entropy? When you throw your box of hot gas into a black hole, the entropy of the universe outside goes down, but the black hole's surface area grows. Bekenstein argued that this increase in area perfectly compensated for the entropy that seemed to have disappeared from view. Stephen Hawking was one of Bekenstein's biggest critics. To settle the matter, Hawking decided to investigate the problem himself. His plan was to look at how quantum mechanics behaved right at the edge of a black hole. He began by considering the nature of empty space. In quantum mechanics, the vacuum is a seething, bubbling foam of energy. Out of this energy, pairs of virtual particles can spontaneously pop into existence. Hawking asked a simple question. What happens to these virtual particle pairs when they appear right on the edge of a black hole's event horizon? The immense gravity could pull the pair apart. This would leave the other particles stranded, alone in the universe outside the black hole. To an observer watching from a safe distance, it would look as though the black hole itself had just spat out a particle. The black hole was not perfectly black after all. It had to glow. This meant that black holes do have a temperature, and therefore they must have entropy. Bekenstein had been right all along. The connection between black hole area, entropy, and temperature was finally cemented in a beautiful and simple equation. It is now known as the Bekenstein-Hawking formula, and it's considered one of the most important equations in fundamental physics. In fact, it's engraved on Stephen Hawking's memorial stone at Westminster Abbey. What makes this formula so revolutionary is that it ties together thermodynamics, relativity, and quantum theory in a single, elegant statement about black holes. The discovery that a black hole's entropy is proportional to its surface area completely overturned our intuition about where information is stored. It suggests that our three-dimensional reality might be a kind of illusion, a hologram. The holographic principle suggests that the universe itself might work this way. The reality we experience might actually be a projection of information that is written on a distant, two-dimensional surface at the edge of the cosmos. The discovery of Hawking radiation completely changed our picture of black holes. A black hole is kind of like a bucket with a very tiny hole in the bottom. It can be filled up by swallowing stars and gas, but it is always, almost imperceptibly, leaking its contents back out into the universe. This leads to a dramatic end for a black hole. As it radiates away its mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates even faster. The black hole goes out not with a whimper, but with a bang. It would end its long life in a final, brilliant flash of high-energy gamma rays and particles, releasing all of its remaining mass back into the universe as energy. This entire process provides a solution to the entropy puzzle that started it all. Over its entire lifetime, the black hole ensures that the second law of thermodynamics is upheld. The cosmic accounting books are perfectly balanced, from beginning to end. We began our journey with a simple puzzle. Black holes seemed to be cosmic outlaws, capable of violating one of the most fundamental laws of nature. The quest to resolve this issue forced scientists to venture into uncharted territory, where the grand theories of gravity and the quantum world collide. What we discovered has been nothing short of a revolution. Black holes are not simple voids, but complex thermodynamic objects. They possess entropy, elegantly encoded on the two-dimensional surface area of their event horizon. Imagine a magical cosmic library card. Every time you add a new book to the library, the surface area of the card gets just a little bit bigger. This is how a black hole seems to work. The event horizon is like this magical library card. The holographic principle suggests that our three-dimensional world could be the holographic projection of that underlying two-dimensional reality. While we don't yet know if the universe is truly a hologram, the physics of black holes has forced us to confront this stunning possibility. While the discoveries of Bekenstein and Hawking solved the original entropy puzzle, they also opened a Pandora's box of new, even deeper questions. The most famous of these is the black hole information paradox. What happens to the unique information that falls into a black hole? Another profound mystery lies at the very center of the black hole, the singularity. We know this cannot be the full story. It is a sign that our theory is incomplete. A true theory of quantum gravity is needed to describe what really happens in this extreme environment. The story of black hole thermodynamics ultimately reshapes our place in the cosmos. It shows us a universe that is not only stranger than we imagine, but stranger than we can even imagine. This new understanding offers a sense of profound connection. It shows that the universe is a unified whole, where the laws governing the infinitesimally small are married to the laws governing the infinitely large. Our quest to understand the universe is a quest to understand the intricate grammar of this story, to see how all the pieces fit together. In the end, the journey into the heart of a black hole is a journey into the heart of knowledge itself. The universe is a vast and complex book, and with every page we turn, we find that the story is more intricate and more beautiful than we could have ever dreamed.